Hello there, and welcome to the Sleepy Science Society. Tonight, we are drifting outward, beyond the familiar boundaries of our world, beyond the comfortable edges of understanding, into the vast and quiet mystery of the cosmos itself. This is a journey that begins at the very edge of knowing and stretches toward infinity. A journey through space so enormous that light itself, traveling at speeds we can barely comprehend, takes billions of years to cross from one side to the other. As you settle in for this gentle exploration, I invite you to like, subscribe, or share a thought below. Your support helps more curious souls find this peaceful corner where science becomes a soft companion to rest. The cosmos is not simply empty space dotted with stars. It is a living, breathing structure of unimaginable complexity and beauty. It is a place where time and space weave together into a fabric that bends, stretches, and ripples, where invisible forces shape the paths of galaxies, where light from the earliest moments of creation still whispers its ancient story across the darkness. Tonight, we will explore this cosmic realm together, moving slowly through its many layers, pausing to wonder at each remarkable discovery. So let your eyes relax, allow your breathing to deepen. Feel the weight of your body settling into comfort, and let your mind drift gently into the infinite. Let us begin at the very beginning, at the moment when everything that is and ever will be suddenly burst into existence. 13.8 billion years ago, in a moment so brief it defies imagination, the entire universe exploded into being. This event, which we now call the Big Bang, was not an explosion in space. It was an explosion of space itself. Before this moment, there was no before. Time, as we understand it, had not yet begun. Space did not exist to contain anything. Matter and energy were concepts without meaning. And then, in less time than it takes light to cross the width of an atom, everything changed. In that first infinitesimal fraction of a second, the universe underwent a period of exponential expansion called inflation. Space stretched faster than the speed of light, carrying with it the seeds of everything that would follow. The universe doubled in size again and again and again, so rapidly that in less time than you could blink, a region smaller than a grain of sand expanded to become larger than the observable universe we see today. This inflationary period solved several puzzles that had troubled cosmologists. It explained why distant regions of the universe, separated by distances so vast that light from one could never have reached the other, nevertheless show the same temperature and properties. They were once close together, in intimate contact, before inflation stretched them apart. When inflation ended, the universe was filled with an incredibly hot, dense soup of fundamental particles and radiation. The temperature was measured not in thousands or millions of degrees, but in numbers so large they become abstract. Protons, neutrons, electrons, and photons swirled together in a plasma so energetic that matter as we know it could not yet form. The universe glowed with a brilliance that would have been blinding beyond comprehension if there had been eyes to see it. But it was expanding and cooling, following the inexorable laws of thermodynamics that still govern the cosmos today. In the first 3 minutes after the Big Bang, The universe cooled enough for protons and neutrons to stick together, forming the nuclei of the lightest elements. Hydrogen nuclei, consisting of single protons, were the most abundant. Some combined with neutrons to form deuterium, a heavier form of hydrogen. A fraction went further, building up helium nuclei with 2 protons and 2 neutrons. Tiny amounts of lithium also formed during this primordial nucleosynthesis. But the universe was expanding too quickly and cooling too fast for anything heavier to appear. The creation of carbon, oxygen, nitrogen, and all the other elements that make up planets and people would have to wait for stars. For 380,000 years, the universe remained too hot for atoms to exist. Electrons could not settle into orbits around nuclei because they moved too quickly, constantly knocked free by energetic photons. Light could not travel far through this thick fog of charged particles. Every photon scattered off electrons after traveling only a short distance, like trying to see through a cloud. But as the universe expanded, it cooled. The temperature dropped from trillions of degrees to billions, then millions, then thousands. Finally, when the universe had cooled to about 3,000 degrees Kelvin, a temperature similar to the surface of a red dwarf star, something remarkable happened. Electrons slowed down enough to be captured by nuclei. Hydrogen atoms formed as electrons found stable orbits around protons. Helium atoms assembled from their nuclei and electrons. For the first time, the universe became transparent. Photons that had been trapped in an endless cycle of scattering were suddenly free to travel unimpeded through space. These photons, released in that moment of cosmic clearing, have been traveling ever since. We detect them today as the cosmic microwave background radiation. Cooled by the expansion of the universe from thousands of degrees to just a few degrees above absolute zero. This ancient light carries with it a detailed map of the infant universe, showing us tiny density variations that would one day grow into galaxies and galaxy clusters. The release of the cosmic microwave background marked the beginning of what cosmologists call the Dark Ages. Not dark because of any sinister quality, but dark because there were no stars yet to light the void. The universe had become transparent, but it was also empty of luminous objects. Only neutral hydrogen gas-filled space slowly collecting under the influence of gravity into increasingly dense clouds. These clouds moved through the expanding universe, drawn together by an invisible force that would prove to be one of the greatest mysteries in all of science. The gravitational pull that gathered hydrogen into clouds was not coming only from the ordinary matter we can see. It was primarily driven by something else, something that does not emit, absorb, or reflect light. Something that interacts with normal matter almost exclusively through gravity. We call it dark matter, and it is one of the most profound puzzles facing modern physics. Dark matter reveals itself through its gravitational effects, even though it remains completely invisible to our telescopes. When astronomers measure how fast stars orbit around the centers of galaxies, they find something unexpected. The stars at the outer edges of galaxies move far too quickly. According to the visible matter alone, these outer stars should be moving slowly, like the outer planets in our solar system orbit the Sun more leisurely than the inner planets. But they are not. They race around at speeds that would fling them into intergalactic space unless something massive and invisible is holding them in place. This invisible something is dark matter. It forms enormous halos around galaxies, extending far beyond the visible stars and gas. These dark matter halos contain several times more mass than all the ordinary matter in the galaxy combined. When we map the distribution of dark matter using gravitational lensing, watching how its gravity bends the light from background galaxies, we see that it forms vast cosmic scaffolding. Like an invisible web spanning the universe, dark matter creates the framework upon which galaxies and galaxy clusters hang. The evidence for dark matter comes from multiple independent sources, each pointing to the same conclusion. Galaxy clusters contain hot gas between their member galaxies, gas so hot it emits X-rays. By measuring the temperature and distribution of this gas, astronomers can calculate how much mass is needed to keep it from escaping. The answer is always far more than the visible matter can provide. In the famous bullet cluster, formed when two galaxy clusters collided, astronomers watched ordinary matter and dark matter separate. The gas clouds from each cluster collided and slowed down, glowing with X-rays from the collision. But the dark matter passed right through, completely unaffected by the collision, betraying its presence only through gravitational lensing. This collision provided perhaps the most direct evidence that dark matter truly exists as a separate component of the universe. But what is dark matter made of? Despite decades of searching, we still do not know. The most popular candidates are weakly interacting massive particles, often called WIMPs. These hypothetical particles would have been created in the hot, early universe and would interact with ordinary matter only through gravity and the weak nuclear force. Experiments buried deep underground try to catch WIMPs as they pass through detectors, but so far, none have been definitively detected. Another candidate is the axion, a much lighter particle originally proposed to solve a different problem in particle physics. Axions would be incredibly numerous, but individually nearly massless, filling space like an invisible ocean. Sophisticated experiments search for the subtle effects actions might produce in strong magnetic fields. Some physicists have proposed that dark matter might not be particles at all, but instead a modification of gravity itself. Perhaps Einstein's general relativity needs adjustment on the largest scales, they suggest. But these modified gravity theories struggle to explain all the observations that dark matter explains so naturally. The cosmic microwave background, the growth of structure in the universe, the behavior of galaxy clusters during collisions, all point toward actual particles rather than modified laws. The search continues, with ever more sensitive detectors, more powerful particle accelerators, and increasingly clever experimental designs. When we finally discover what dark matter is made of, it will rank among the greatest scientific discoveries in human history. Dark matter accounts for approximately 27% of the total mass and energy content of the universe. Ordinary matter, everything made of atoms including stars, planets, gas clouds, and every living thing, makes up only about 5%. The remaining 68% is something even more mysterious than dark matter. It is called dark energy. and it represents perhaps the deepest mystery in all of cosmology. In 1998, two teams of astronomers studying distant supernovae made an announcement that shocked the scientific world. They had been measuring how fast the universe was expanding at different times in cosmic history by observing special exploding stars called Type Ia supernovae. These stellar explosions have a consistent brightness, making them excellent distance markers. By comparing their apparent brightness to their known actual brightness, astronomers can calculate how far away they are. By measuring their redshift, how much their light has been stretched by the expansion of space, astronomers can determine when in cosmic history the explosion occurred. Everyone expected that the expansion of the universe would be slowing down. After all, every galaxy pulls on every other galaxy through gravity. This cosmic tug-of-war should gradually decelerate the expansion, just as a ball thrown upward slows as Earth's gravity pulls it back. Some thought the expansion might slow enough to eventually reverse, leading to a big crunch. Others thought it would slow but never quite stop, leading to eternal expansion. But no one predicted what the supernova teams actually found. The universe's expansion is accelerating. Galaxies are not just moving apart, they are moving apart faster and faster as time goes on. This acceleration implies the existence of something pushing space apart, something with properties unlike any form of matter or energy known to physics. The teams called it dark energy, and subsequent observations have only strengthened the case for its existence. Dark energy has a bizarre property that distinguishes it from all other forms of energy. Its density remains constant even as the universe expands. When ordinary matter spreads out as space grows, its density drops proportionally. Radiation becomes even more diluted, losing energy as its wavelengths stretch. But dark energy maintains the same density no matter how much the universe grows. This means that as the universe expands, the total amount of dark energy increases, while the density of matter and radiation continues to fall. Eventually, dark energy came to dominate the universe's energy budget, and its repulsive effect began driving accelerated expansion. The simplest explanation for dark energy is that it represents the energy of empty space itself. Quantum mechanics suggests that even the vacuum of space is not truly empty. Virtual particles constantly pop into and out of existence, creating a background energy that persists everywhere. Einstein's equations of general relativity include a term called the cosmological constant that represents exactly this kind of uniform energy filling all of space. Einstein originally added this term to keep the universe static in his equations, but later abandoned it, reportedly calling it his greatest blunder. The supernova observations vindicated the cosmological constant, though not in the way Einstein imagined. If dark energy is indeed a cosmological constant, then its density will remain unchanged forever, continuing to accelerate the expansion of the universe for all time. Galaxies beyond our immediate neighborhood will be carried away from us ever faster. Eventually, they will recede at speeds greater than light, disappearing beyond a cosmic horizon from which no light can ever reach us. Our distant descendants, billions of years from now, might look out into space and see only the galaxies of our local cluster. bound together by gravity against the expansion. All other galaxies will have vanished beyond the edge of the observable universe. But dark energy might not be constant. Some theories propose that it changes with time, growing stronger or weaker as the universe evolves. These models involve exotic fields pervading space, similar to the field that drove inflation, but much weaker. Astronomers probe the history of cosmic expansion with increasing precision, measuring distances and redshifts for galaxies at many different cosmic epochs, searching for any hint that dark energy is evolving. Recent observations from the Dark Energy Spectroscopic Instrument have provided tantalizing hints that dark energy might indeed be dynamic rather than constant, though these results require confirmation. If dark energy weakens over time, the universe might eventually stop accelerating. If it strengthens, the acceleration could become so extreme that it tears apart first galaxy clusters, then galaxies, then star systems, and finally atoms themselves in a catastrophic Big Rip. The nature of dark energy shapes not only the future of the universe, but also its past. Dark energy's influence was negligible in the early universe, when matter and radiation were much denser. But as the universe expanded and matter diluted, dark energy gradually became more important. About 5 billion years ago, dark energy's repulsive effect finally overcame the attractive pull of gravity, and cosmic expansion began to accelerate. We live in a time of transition, when dark energy has just taken control of the universe's fate. The competition between dark matter's gravitational attraction and dark energy's repulsive push determines the large-scale structure of the universe. In the early cosmos, tiny density fluctuations in the distribution of dark matter, imprinted during the inflationary epoch, began to grow under gravity. Regions that were slightly denser than average attracted more matter. The extra matter made them denser still, allowing them to attract even more. This process of gravitational instability amplified small perturbations into larger and larger structures over billions of years. Dark matter, interacting only through gravity, could clump together easily without any resistance. It formed the scaffolding, the invisible framework that shaped the cosmos. Ordinary matter, influenced by pressure and radiation, took longer to settle into the gravitational wells created by dark matter. But eventually, hydrogen gas flowed into these wells, forming clouds that grew dense enough to collapse and ignite into stars. These first stars, born perhaps 100 million years after the Big Bang, ended the cosmic dark ages and began the age of galaxies. As structure continued to grow, dark matter and gas collected into increasingly complex patterns. The cosmic web emerged, a magnificent architecture spanning billions of light years. In this web, matter is not distributed uniformly, but instead concentrates along filaments and sheets, leaving vast voids in between. The filaments, made primarily of dark matter with ordinary matter tracing the same patterns, connect at nodes where galaxy clusters form. These clusters contain hundreds or thousands of galaxies bound together by mutual gravity. Between the filaments stretch enormous voids, regions of space with very few galaxies. Some voids span hundreds of millions of light years across. They are not completely empty. containing diffuse gas and perhaps the occasional lonely galaxy, but they represent deserts in the cosmic landscape. The voids and the dense structures between them form a pattern that cosmologists describe as resembling soap bubbles or foam, with galaxies sitting on the surfaces while the interiors remain largely empty. The largest structures in the universe are superclusters and galactic walls. Superclusters are groupings of galaxy clusters, connected by filaments and sheets of galaxies. Our own Milky Way resides in a relatively small cluster called the Local Group, which itself belongs to the Virgo supercluster, which is part of an even larger structure called the Laniakea supercluster. This vast complex of galaxies, spanning 520 million light-years, flows together under mutual gravitational attraction. Astronomers discovered Laniakea by mapping the motion of galaxies, finding that everything in this enormous region is being drawn toward a central point called the Great Attractor. Even larger than superclusters are galactic walls, vast sheets of galaxies stretching across hundreds of millions or even billions of light-years. The Sloan Great Wall, discovered in 2003, spans about 1.4 billion light-years. Though truly enormous, these walls are relatively thin, only about 20 million light-years in depth. They represent the edges of voids, places where multiple filaments come together to form a two-dimensional surface. From a distance, if we could see the entire observable universe at once, these walls would look like gossamer threads connecting the densest nodes in the cosmic web. This large-scale structure formed through a beautiful interplay of physics. The initial density fluctuations, quantum ripples amplified by inflation, provided the seeds. Dark matter's gravity pulled these seeds into increasingly dense concentrations. Ordinary matter fell into the dark matter wells, sometimes colliding and shocking into heated gas, sometimes cooling and fragmenting into stars. Dark energy's repulsive effect worked against structure formation, smoothing out small fluctuations and eventually halting the growth of the largest structures. The result is a cosmic architecture that records the entire history of the universe, from the quantum fluctuations of the inflationary epoch to the present-day dominance of dark energy. Galaxies are the building blocks of this large-scale structure. Islands of billions or trillions of stars held together by gravity. They come in a remarkable variety of forms. Spiral galaxies, like our own Milky Way, feature rotating disks of stars, gas, and dust, arranged in graceful arms that spiral outward from a central bulge. These arms trace regions where gas compresses and triggers waves of star formation, creating bright young stars that light up the spiral pattern. Between the arms, stars continue to orbit, but they are often older and dimmer, so the arms stand out prominently. Elliptical galaxies lack the organized disk and spiral structure. They appear as smooth, featureless ellipses containing mostly older stars. Some are nearly spherical, while others are quite elongated. Elliptical galaxies form through mergers of smaller galaxies, violent collisions that stir up the stars and destroy any organized rotation. The largest galaxies in the universe are giant ellipticals at the centers of galaxy clusters, enormous systems containing trillions of stars formed through multiple mergers over cosmic time. Irregular galaxies defy easy classification, appearing chaotic and disorganized. They often form through gravitational interactions with neighboring galaxies, tidal forces pulling stars and gas into distorted shapes. Some irregular galaxies are small dwarf systems, modest collections of stars that orbit larger galaxies as satellites. Our Milky Way has dozens of dwarf galaxy companions, the largest being the Large and Small Magellanic Clouds visible from the southern hemisphere. At the heart of every large galaxy lies a supermassive black hole, an object containing millions or billions of times the mass of our Sun compressed into an infinitesimally small point. These black holes profoundly influence their host galaxies. When gas falls toward a supermassive black hole, it forms a swirling accretion disk that heats to millions of degrees, shining brilliantly in X-rays. Jets of particles and energy can shoot outward from near the black hole at nearly the speed of light, extending for millions of light-years beyond the galaxy. These active galactic nuclei, as astronomers call them, can outshine the entire galaxy and affect star formation throughout the galaxy and beyond. The relationship between black holes and their galaxies represents one of the most intriguing puzzles in astrophysics. The mass of the supermassive black hole correlates tightly with properties of the galaxy's central bulge. Somehow, across hundreds of thousands of light-years, the black hole and the stars communicate and regulate each other's growth. Perhaps bursts of energy from the actively feeding black hole heat gas throughout the galaxy, suppressing star formation. When the black hole runs out of fuel and goes quiet, the gas can cool and form new stars. This feedback cycle may repeat many times over a galaxy's life, shaping its evolution. Galaxies evolve dramatically over cosmic time. When we look at distant galaxies, seeing them as they were billions of years ago, because of light's finite travel speed, we see differences from nearby galaxies. Young galaxies are often smaller, more chaotic, and more actively forming stars than galaxies today. They undergo frequent mergers and interactions as the universe is more densely packed. Over billions of years, these small galaxies merge and grow, eventually settling into the mature spirals and ellipticals we see in the nearby universe. The Milky Way, our cosmic home, is a large spiral galaxy containing between 100 and 400 billion stars. Our Sun orbits the galactic center at a distance of about 26,000 light-years, taking approximately 230 million years to complete one orbit. From our vantage point within the disk, the Milky Way appears as a band of light across the night sky, the combined glow of billions of distant stars. Ancient observers saw this band and imagined it as spilled milk across the heavens, giving our galaxy its name. The Milky Way's structure consists of several components. The disk contains most of the stars, gas, and dust, organized into several spiral arms. At the center sits a bar-shaped structure of older stars with the supermassive black hole, called Sagittarius A star, lurking at its heart. This black hole contains about 4 million solar masses, but remains relatively quiet, accreting matter slowly and producing only modest amounts of radiation. Surrounding the disk is a spherical halo of old stars and globular clusters, dense balls of hundreds of thousands of ancient stars born in the galaxy's youth. The halo extends far beyond the visible stars, dominated by the invisible dark matter that holds the galaxy together. In a few billion years, the Milky Way will collide with our nearest large neighbor, the Andromeda Galaxy. Despite the dramatic name, galactic collisions are actually quite gentle for the stars themselves. Galaxies are so empty that stars pass by each other without colliding. But the gravitational forces reshape both galaxies, pulling out tidal tails of stars and gas, triggering intense bursts of star formation where gas clouds collide, and eventually merging the two galaxies into a single giant elliptical. Our Sun will survive this merger unscathed, though it will end up in a very different environment, perhaps flung into the outer reaches of the merged galaxy or settling into the dense core. The observable universe contains an estimated 2 trillion galaxies, each a vast collection of stars with its own unique history. Yet all these galaxies, all this structure, emerges from the interplay of a few fundamental components and forces. Gravity pulls matter together. Dark matter provides the gravitational scaffolding. Dark energy pushes space apart. Normal matter forms stars and planets. Radiation carries energy across vast distances. And all of it unfolds against the backdrop of space-time itself. The four-dimensional fabric that Einstein revealed to be dynamic and curved by mass and energy. General relativity, Einstein's theory of gravitation, describes space-time as a geometric structure that bends in the presence of mass and energy. This curvature is what we experience as gravity. Massive objects like stars and galaxies curve space-time around them, and other objects follow curved paths through this warped geometry. Light itself follows the curvature, bending around massive objects in an effect called gravitational lensing. On cosmic scales, the geometry of space-time determines the ultimate fate of the universe. General relativity allows for 3 possible geometries. A closed universe has positive curvature, like the surface of a sphere. In such a universe, parallel lines eventually converge, and the universe is finite in size, though without boundaries. An open universe has negative curvature, like a saddle shape, with parallel lines diverging. A flat universe has 0 curvature, with the familiar geometry of Euclidean space. Observations of the cosmic microwave background and the large-scale structure of the universe indicate that our universe is very nearly flat. The total energy density is almost exactly equal to the critical density needed for flatness. This flatness was one of the original motivations for inflation theory. Without inflation to drive the universe very close to flatness in its earliest moments, it would have quickly curved away from flatness as it evolved. Yet we observe near-perfect flatness today, suggesting something set the initial conditions with exquisite precision. Inflation provides that something, driving the universe so close to flatness that even after 13.8 billion years of evolution, we cannot detect any curvature. Space-time itself is not static. It can ripple and wave, carrying energy through gravitational waves. When massive objects accelerate, especially in violent astrophysical events like colliding black holes or neutron stars, they create ripples in space-time that propagate outward at the speed of light. These gravitational waves stretch and squeeze space as they pass, alternately lengthening and shortening the distance between objects by tiny amounts. Einstein predicted gravitational waves in 1916, but they were not directly detected until 2015, nearly a century later. The detection came from the Laser Interferometer Gravitational Wave Observatory, or LIGO, which uses laser beams bouncing between mirrors separated by several kilometers to measure minute changes in distance. When gravitational waves from two colliding black holes passed through Earth, they altered the distance between LIGO's mirrors by less than 1,000th the diameter of a proton. Yet this astonishingly small signal was enough to confirm the wave's existence and open a new window onto the universe. Since that first detection, scientists have observed dozens of gravitational wave events, including colliding black holes of various masses, merging neutron stars, and possibly other exotic phenomena. Gravitational waves carry information about the universe that is completely independent from electromagnetic radiation. They allow us to study objects and events that produce little or no light, to probe the interiors of extreme gravitational fields where light cannot escape, and to test general relativity in regimes of incredibly strong gravity. Future gravitational wave detectors, both on the ground and in space, will observe signals from across cosmic history, potentially detecting gravitational waves produced during inflation itself. Carrying information about the universe's first fraction of a second. The universe has a history written in light and structure. By observing galaxies at different distances, which means at different times in the past, astronomers trace how the cosmos has evolved. Very distant galaxies, seen as they were when the universe was young, appear small and irregular, often undergoing intense bursts of star formation. Intermediate distance galaxies show more organized structure as they settle into mature forms. Nearby galaxies represent the present epoch, where star formation has slowed in many galaxies and structures have stabilized. The cosmic timeline stretches from the Big Bang to the present day and beyond into the future. In the first fraction of a second, inflation stretched space exponentially. In the first few minutes, the lightest atomic nuclei formed. After 380,000 years, atoms formed and the universe became transparent. The first stars ignited after about 100 million years, ending the Dark Ages. Galaxies assembled and grew through mergers and accretion over billions of years. About 5 billion years ago, dark energy began dominating the universe's expansion. Today, 13.8 billion years after the Big Bang, we find ourselves in a mature universe still evolving, with active star formation continuing, but gradually slowing as galaxies exhaust their gas supplies. The chemical composition of the universe has evolved dramatically since the Big Bang. Initially containing only hydrogen, helium, and trace lithium, the universe has been progressively enriched with heavier elements by successive generations of stars. Massive stars forge carbon, oxygen, nitrogen, and other elements through nuclear fusion in their cores. Then scatter these elements into space when they explode as supernovae. Neutron star mergers create the heaviest elements like gold and platinum through rapid neutron capture. Each new generation of stars forms from gas that contains more heavy elements than the previous generation, making possible the rocky planets and complex chemistry that support life. Our Sun and solar system formed about 4.6 billion years ago from a cloud of gas enriched by countless previous stellar generations. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in stellar interiors or explosive cosmic events long before Earth existed. We are, quite literally, made of star stuff, assembled from elements created across billions of years of cosmic evolution. This connection to the broader cosmos links us intimately to the history of the universe itself. Looking forward, the future of the cosmos depends on the nature of dark energy. If dark energy is truly a cosmological constant, the accelerated expansion will continue forever. Galaxies outside our local group will disappear beyond the cosmic horizon. Star formation will gradually cease as galaxies exhaust their gas. Existing stars will age and die. In trillions of years, the last stars will flicker out, leaving behind white dwarfs, neutron stars, and black holes orbiting in eternal darkness. Eventually, even black holes will evaporate through quantum effects called Hawking radiation. The universe will approach a cold, empty state where nothing changes and no structures remain. But this far future might never come if dark energy evolves. If it strengthens with time, it could rip apart bound structures, first galaxy clusters, then galaxies, then solar systems, and finally atoms themselves in a big rip. If it weakens and eventually reverses, the expansion could halt and reverse, leading to a big crunch where the universe collapses back to a hot, dense state. Some speculative theories even suggest the universe could undergo cycles of expansion and contraction, each cycle potentially creating a new universe with different properties. The far future remains fundamentally uncertain, one of the deepest mysteries in all of science. The observable universe, the region from which light has had time to reach us since the Big Bang, extends about 46 billion light-years in every direction. This distance is larger than 13.8 billion light-years because space itself has been expanding during the time the light traveled toward us. Beyond this cosmic horizon lies more universe, regions from which light has not yet reached us and perhaps never will, if the accelerating expansion continues. We cannot observe these regions directly, cannot know what lies beyond the edge of visibility, cannot determine whether the universe is finite or infinite. Yet we can learn something about the larger cosmos through the cosmic microwave background. The patterns in this ancient light show us that the universe is extremely uniform on large scales, with the same properties in every direction. If we could see beyond our observable patch, we would likely find more of the same, more galaxies, more voids, more structure formed through the same physical processes that shaped our region. The observable universe is probably not special, just one patch in a much larger cosmos. Some theoretical physicists speculate about even grander structures beyond our universe. The multiverse hypothesis suggests that our cosmos might be just one bubble in an infinite foam of universes, each with potentially different laws of physics, different values for fundamental constants, even different numbers of dimensions. If inflation is eternal, continuing in some regions of space even as it ends in others, new universes might continually bud off from the inflating background. we could never observe these other universes directly, making the multiverse idea controversial among scientists who argue that science should focus on testable predictions. Yet, the mathematical structure of some theories, particularly string theory, seems to naturally produce multiverses whether we want them or not. Within our observable universe, we can trace our cosmic address with increasing specificity. Earth orbits the Sun, one star among hundreds of billions in the Milky Way. The Milky Way belongs to the local group, a small cluster of more than 50 galaxies, dominated by the Milky Way and Andromeda. The local group lies at the edge of the Virgo supercluster, a complex of galaxy clusters and groups. Virgo, in turn, forms part of the Laniakea supercluster, our cosmic neighborhood extending 500 million light-years. And Laniakea sits within the larger cosmic web of filaments and voids that fills the observable universe. At each level, we zoom out to reveal ever larger structures until, finally, we reach the scale of the observable universe itself, the largest structure we can meaningfully discuss. This nested hierarchy of structure, from planets to solar systems to galaxy clusters to superclusters to the cosmic web, all emerged from simple initial conditions and fundamental forces. The seeds planted during inflation grew through gravitational amplification. Dark matter provided the framework. Ordinary matter filled in the details. Stars formed and evolved and died, enriching the cosmos with heavy elements. Life arose on at least one planet, perhaps many more, and consciousness emerged, allowing the universe to contemplate itself. The pale blue dot photograph, taken by Voyager 1 from beyond Neptune, shows Earth as a tiny point of light suspended in a sunbeam, barely distinguishable from countless other photons in the image. Carl Sagan reflected on this image, noting how it reveals the insignificance of human affairs against the backdrop of cosmic vastness. Every human who ever lived, every triumph and tragedy, every war and peace played out on this mote of dust suspended in space. The cosmos pays no attention to our concerns. It operates according to physical laws that care nothing for human hopes or fears. Yet we are not separate from the cosmos. We are part of it, expressions of its ability to create complexity and consciousness. The same atoms that make up distant galaxies flow through our bodies. The same forces that govern stars and black holes also hold our atoms together. We emerged from the universe. Temporary patterns of organization created by the flow of energy from hot to cold. Our thoughts arise from electrical impulses in neural circuits, quantum effects in molecular structures, all obeying the same physical laws that govern everything else. In understanding the cosmos, we understand ourselves. The cosmic perspective, this view of ourselves as part of something incomprehensibly vast and ancient, can be humbling but also inspiring. It reminds us that we share this planet, this solar system, this galaxy with each other, that our differences pale in comparison to what unites us. It reveals that we are remarkably improbable, the product of 13.8 billion years of cosmic evolution, the beneficiaries of countless fortunate circumstances. It suggests that we should cherish our existence, protect our world, and continue exploring the universe that gave us birth. Every photon entering your eye from a distant star began its journey years or centuries or millions of years ago. The light from the Andromeda Galaxy left 2.5 million years ago, when our ancestors were early hominids just learning to use tools. Light from distant quasars has traveled for billions of years, showing us the universe as it was when the first galaxies were forming. When we look into deep space, we look backward through time, watching cosmic history unfold. The present moment, as we experience it, is a constantly shifting surface where past light cone meets future light cone, where ancient photons arrive to illuminate the now. The cosmos continues its grand evolution regardless of whether we observe it. Stars are forming this moment in distant galaxies, collapsing from clouds of gas and dust into glowing spheres of fusing hydrogen. Supernovae are exploding, scattering their enriched contents into space where new stars will form. Black holes are merging, radiating gravitational waves that ripple through space-time. The cosmic web continues its slow evolution as structure grows under gravity's influence and dark energy pushes the expansion ever faster. The universe persists in being, moment by moment, following the laws of physics from the quantum to the cosmic scale. We stand at a privileged moment in cosmic history. The universe is old enough that rocky planets and complex life could form, yet young enough that stars still shine and galaxies still fill the sky. 100 billion years from now, the accelerating expansion will have carried most galaxies beyond the cosmic horizon. Observers in that distant future will see only their local galaxy cluster floating in an apparently empty void. They will have no evidence that the universe is expanding, no cosmic microwave background to study, no distant galaxies to observe. They might conclude they live in a static, eternal universe, never suspecting the rich cosmic history that preceded their epoch. We are fortunate to live when the universe reveals its history so clearly. The scientific understanding of the cosmos represents one of humanity's greatest intellectual achievements. Through observation, experimentation, and theoretical insight, we have pieced together a coherent picture of the universe from the Big Bang to the present day. We have discovered phenomena we never imagined, like dark matter and dark energy and gravitational waves. We have learned that the cosmos is far stranger and more wonderful than anyone could have guessed. And yet vast mysteries remain. The nature of dark matter, the origin of dark energy, the physics of the Big Bang itself, the possibility of other universes. These questions push at the boundaries of current knowledge, inviting future generations to continue exploring. As you rest here, breathing slowly, feeling the peace of this moment, remember that you are part of this grand cosmos. The atoms in your body were forged in stars. Your consciousness is a temporary pattern emerging from the complex interplay of physics and chemistry. Your existence depends on 13.8 billion years of cosmic evolution, on dark matter shaping the galaxies, on stars creating elements, on planets forming in stable orbits, on the physical constants being just right to allow complexity. You are stardust contemplating the stars, a way for the cosmos to know itself. The universe is vast beyond comprehension. It contains more stars than grains of sand on all Earth's beaches. It spans distances so enormous that light takes billions of years to cross them. It operates on timescales from the infinitesimal fractions of a second during inflation to the inconceivable trillions of years before the last stars fade. And yet, for all its grandeur, the cosmos can be understood. The laws of physics that govern distant galaxies are the same laws we can study in laboratories on Earth. The mathematics that describes space-time curvature near black holes is an extension of the same geometry we learn in school. The universe is comprehensible, and we are comprehending it. If you have enjoyed this quiet journey through the cosmos, I invite you to like this video, subscribe to the channel, or share your thoughts in the comments below. Your engagement helps more people discover these peaceful explorations of science. It supports the creation of future videos that blend wonder and knowledge with calm and rest. For now, let the vastness of the cosmos embrace you. Feel yourself floating in space, a tiny mote of consciousness adrift in the infinite. The same atoms that make distant nebulae glow with colors we cannot name flow through your veins. The same fundamental forces that bind galaxies together hold your body intact. You are cosmically connected to everything that is, was, or ever will be. You are the universe experiencing itself, a brief flowering of awareness in the long cosmic story. Let your thoughts drift like galaxies moving through space. Let your breathing slow, like the expansion of the universe in its earliest moments. Let your awareness settle into the deep stillness that exists beneath all motion, the quiet foundation from which all existence emerges. The cosmos continues its ancient dance, stars forming and dying, galaxies spinning through the void, gravitational waves rippling through space-time. And you rest here, part of it all, experiencing this moment of peace. The journey through the cosmos has brought us far from home, yet everything we encountered connects back to this moment, this breath, this peaceful resting place. The universe is not somewhere else. It is here, now, in you. Every breath draws in atoms from distant stars. Every heartbeat echoes the rhythms of cosmic processes. Every thought reflects the complexity that emerged from simple beginnings 13.8 billion years ago. You are not separate from the cosmos. You are its expression, its consciousness, its way of knowing itself. As you settle into sleep or into quiet contemplation, let the wonder of existence fill you with gratitude. We are here, briefly, improbably, beautifully. We can see the stars and ponder their nature. We can trace the evolution of the universe through mathematics and observation. We can feel the connection that binds us to everything that exists. This knowledge, this awareness, this moment of understanding, it is a gift granted by the cosmos to itself. The stars shine tonight as they have shone for billions of years, indifferent to our watching, yet beautiful beyond words. The galaxies spiral through space, following paths laid down by invisible dark matter. The cosmic web stretches across hundreds of millions of light years, connecting everything to everything else. And somewhere, on a small rocky planet, orbiting an ordinary star in an unremarkable galaxy, consciousness arose and learn to contemplate the vast cosmos from which it emerged. Sleep now, cosmic traveler. Dream of distant galaxies and ancient light. Rest in the knowledge that you are part of something infinite and eternal. Let the universe cradle you in its vast embrace. Let the peace of cosmic awareness settle into your bones. You have journeyed far tonight, through space and time, through mystery and wonder. You have touched the infinite. Now, gently, softly, let it all go. Simply rest. Simply be. The cosmos will continue its dance while you sleep. The stars will keep their vigil. The universe will persist in being. And you, for now, can simply rest in the quiet darkness, part of everything, aware of nothing, at peace. Good night, fellow star child. Good night.